Yeah, so in figure 27-35, resistor 1 is equal to 100 ohms, resistor 2 is equal to 50 ohms, and the ideal batteries have EMFs. EMF 1 is equal to 6 volts, EMF 2 is equal to 5 volts, and EMF 3 is equal to 4 volts. Find A, the current in resistor 1, B, the current in resistor 2, and C, the potential difference between points A and B.
So this is one of the example problems from your textbook too. This is a typical case of the DC circuit. You can maybe apply the junction rule and the loop rule too. So the circuit consists of three EMF, batteries and like two resistors. So you can, and also like there are two separate current loops. So you can apply the two separate loop rules. So for number 1A, let me change the color. So if you look at this, the number this, so basically there's two loops, right? There's one loop inside of this bottom part of the circuit, and there's the second loop in this upper part of this circuit. So if you look at the loop 1, this one could be loop 1, that's loop 2. If you look at loop 1, along the current path with the orientation of the loop 1, you can find out the potential rise and the potential drop by battery and EMF and resistor R1. So that should be like this R1 E2 minus I1 times the R1 should be equal to 0, because as you guess, the so basically now if you look at the current path from the E2, that the current flow is the same direction, that is I1, with the orientation of loop 1. So in that case, the battery should create the potential rise because the direction are same, and the resistor should create a negative potential drop. So based on that, you should have this relationship. From that, I1 should be E2 over R1. So if you plug that number, so the E2 is 55 volts and R1 is 100 ohm. So the currents through this resistor R1 is 0.05 amps. And now switch to the number B. We have to find the current in the resistor 2. So same thing, you have to apply the loop rule. So now if you look at the orientation of the loop 2, then the E1, E2 and E3, see that direction of their the E2 and E3 is opposite direction of loop 2. But the only E1 is the same direction of loop 2. So in that case, E1 should have the positive sign, but E2 and E3 should come with the negative sign. And now the current flow, assuming that you current flowing that the counterclockwise, then R2 also has same direction with loop 2. In that case, that resistor should comes with the negative sign, like this. So you have that relationship out of the loop rule. So I2, based on that, should be E1 minus E2 minus E3 over R2. You plug the numbers into this formula, then it should be 6 volt of E1 minus E2 is 5 volt, and E3 is 4 volt. Divided by R2, the R2 is 50 ohm. Plug all the numbers, then that has minus 0.06 amps. Here, minus sign indicating that actually just negative actually direction. So you assume that the loop 2 is counterclockwise. I mean the counterclockwise, but you have negative sign. So basically that current should have clockwise, because that comes with the negative sign with respect to the convention of the loop 2. Okay, so negative sign indicating that the direction of current in opposite direction of loop 2. So absolute value of I2 current value is 0.06 amps, 60 milliamps. And now number C, the potential difference between point A and B. So let me just clear up this picture.
Wait, I'm a little confused
Yeah.
on why you subtracted, like use negative signs in front of E2 and E3, because isn't it going in the direction of the current? So it's E1 plus E2 plus E3 minus IR2.
You may want to look back the lecture part I gave you. So basically, if the loop, in the case that the current direction of current is the same as the loop of the direction of the loop, then usually battery or EMF create current, I mean the potential rise, which means you have to put the plus sign before battery. But if the current along that battery, or EMF along battery EMF, if the current is opposite direction to the loop, then that battery should comes with a minus sign, because that create the potential drop.
Wait,
So that's kind of rule. That's
Yeah.
rule.
But in this case, isn't the current going in the same direction as the
Why do you think that? We just staying with this circuit. So see that? Let me change the color. We stay in this circuit, right? So first I set up the direction of the loop with counterclockwise, loop 2. I mean, you can choose any direction actually. Just you can choose the clockwise, you can choose the counterclockwise, but I choose the counterclockwise as the direction of the loop. And now I just, as I said, now when you look at loop, that direction of the loop is same as the E1, right? But just take a look at the E2 and E3. Their sign is opposite. When you take a look at this here, that is flow of current, the plus and minus. That's sign, the direction of the battery, but the direction of loop is this direction.
I remember in the lecture that my teacher gave us, she said for the EMFs, you always want to go from low potential or high potential to
No. That's depend on which direction you choose for the loop. If you choose a loop, you can, as I said, you can set up any direction of the loop. But if your direction of the loop is same direction of the battery, then that should comes with the plus sign. But if that loop direction of the loop is opposite to the path of the battery or path of the current along that battery, then that potential that should have that battery should create the minus sign. So it's pretty relative actually sign, because you see that this one, the E1, the same direction of the loop you set up, and E2 and E3, they're opposite direction of loop 2.
Okay.
See that there's there are three batteries, right? One on the top, the other two bottom, and now you have counterclockwise loop, and this one should come minus to the plus, right? Along, you take a look at the direction of the loop, then there's comes from the minus sign to the plus sign, same direction. Polarity of this battery, the same direction of this loop you set up. But this one, when you just go along this loop, this plus to the minus. That's a negative sign. So relative to this E1, the E2 should have the minus sign. This one too, E3 is plus to the minus. So it comes with the minus sign. Same thing. If you choose, you can choose the actually opposite direction. Like you can choose the loop 2 in different direction clockwise. So let's take a look at the what create the potential rise, potential drop if you choose the different direction of the loop. So if you choose this direction as loop, then loop 2. Then this one, see, the E2 comes with minus to the plus. E3 same. Minus to the plus is same direction of loop 2. So that should comes with E2 plus E3. But take a look at the E1. That's loop in the opposite direction. So batteries is set up with the plus to the minus opposite direction to loop. So that should come with minus E1. So that should be minus E1 plus E2 plus E3. But you have to also choose the sign of R2. So here you choose that direction of R2. So the current flow is actually opposite direction to the R2. So that should comes with the IR2 plus IR2 equals 0. So that's actually create the same relationship with this formula. So if you choose the clockwise as direction of the loop, then the sign of the E1, E2, E3, and R2 will be like this: minus, plus, plus, plus equals 0. So doesn't make any difference. Regardless of which direction you choose in your loop, results should be the same as before.
Mm-hmm.
So it's independent of the direction of the loop, as long as you equally apply the loop rule to the fraction of the circuits, part of the circuit in the same convention. Okay, does it make sense? Or okay, all right. Okay, then number C, potential difference between point A and B. So now let me clear up one more time. So point A right there and point B right there. So 2 points. So any type of potential drop or potential rise should consist of absolute potential value at those 2 points plus 2 battery. Only like between A and B, only 2 battery actually engage into the potential change. So that comes with E3 plus E2. So the potential difference between these two plots actually should be better to re-express this equation by potential of point A minus potential of point B, which is potential variation along the point A and B, is the same as the potential rise or drop created by these 2 batteries. Okay, so now you just add the value into this formula, simple formula. So it's pretty straightforward. So that is 5 volt plus 4 volt. So 9 volt increase. You are going along this direction from the point B to the point A. So if you goes along the same direction of point B to the point A, then you have to have 9 volt potential increase by these 2 batteries. But if you goes along the opposite direction from the point A to the point B, there should the potential drop by these 2 batteries based on that convention.
Wait,
Okay.
so point A to point B, it would increase, and then from point B.
Yeah, point B to the point A, because you are along the same direction of the batteries. So 9-volt increase from point B to the
Oh,
point A. So
okay.
potential variation by the two batteries and the same as potential difference between the two spots. Okay. Any question?
Because they're capacitors and they're in series, does that have anything to do with that, or do you just add the
There's
resistors?
no capacitors.
Oh, they're EMF. Oh, sorry.
There's no capacitor. There's all just they're all just EMF. Electromotive force like batteries or some energy source to give the current flow into the circuits.
Okay,
So,
yeah.
all right. Okay, let's move on. So now 32. I just accidentally captured this image, but this has nothing to do with this problem. Can you read the 32?
Yeah. So both batteries in figure 27-43A are ideal. EMF E1 of battery 1 has a fixed value, but EMF E2 of battery 2 can be varied between 1 volts and 10 volts. The plots in figure 27/43B give the currents through the two batteries as a function of EMF 2. The vertical scale is set by I subscript S is equal to 0.2A. You must decide which plot corresponds to which battery. Before both plots, a negative current occurs when the direction of the current through the battery is opposite the direction of that battery's EMF. What are the A EMF 1 and B resistance R1 and C resistance R2?
So this is similar with the previous problem, but the one difference is their resistor with the varying resistance. So they create a different potential change in terms of their potential drop or potential rise. So this problem provides the current of the current versus the E2. So if you look at this graph at the bottom, the solid black line is E2 plot, and the dashed line is E1 plot. Okay, so there's a two current flow into this circuit. One is from that one is in the loop 1 and this direction, and then this one is also has second loop. So that is, I guess this one is a loop. Let me take a look. Okay, yeah, this is this should be loop 2, and this one is loop 1. So we have to separately apply the junction rule and the loop rule to the two separate loops. So let's take a look at the number 1. So we have to first apply the loop rule for loop 1. You apply it, then E2 now. Let's see. Hold on. Okay, why not just, I can maybe just set up the same direction of the loop with the current flow, because if you just focus on the loop 1, then this battery create the current flow clockwise, so you can think of that as I1. And for sake of the convention, I mean, for sake of the clarification, you can actually set up the loop 1 in the same direction with the I1. So if that is the case, battery 2 create a positive potential drop, I mean potential rise, and just it go along that the current path. Okay, yeah, then that should be I1 R1 minus I1 equals 0. So because that's a loop, and if you look at this current flow along this one, that should be upward, because you see that this E1 produces the current in the upward. So that is the I2. So that should be like this. And then Now, as I said, oh, actually, so the E1 is constant potential, but E2 is varying over time. So depending on the current flow. So now from this relationship, I1 equals E1 minus E2, as you can see, and over R1. From that, so let's see. Yes. This one, if epsilon 2 is larger than epsilon, I mean E2 is larger than E1, then that should be smaller than 0. So now let's take a look at number 1. So number 1 and the battery's EMFs. So we have to find the E1. So that is now E1 and E2, they're same as 6 volt. So if you take a look at this one right there, then this one is I1 equals 0. And the B, when the epsilon, I mean E2, 6, if it's 6, E2 is 6 volt, I mean, sorry, 2 volt. And then you got to take a look at the graph. And 2 volts somewhere is 1, 2 right there. So let's take a look at the I1. Then I1, so this one is I1. I1 is about 0.2. This is 0.1 and this is 0.2. So the I1 itself is 0.2 amps, 20 milliamps. So from that, R1 should be epsilon 1 minus epsilon 2 of I1, right? So that should be 6 volts minus 2 volts divided by 0.2. So R1 should be 4 over 0.2. That is the 20 ohm. Okay. So that the graph is a reference to find out the values for varying, the battery with the potential variation. And the number C, we have to find out resistance R2. So let's take a look at the one of the reference points. So if you take a look at 0.4 volts, so E2, when E2 is 4 volts, then I1 is 0.1, right? So here's 0.1 right there. I1 is 0.1 amps, and I2 is the 0. So we just randomly pick up the current values and at arbitrary point of the E2 to find out the R2. So here, R2, if you look at the loop 2, then that is based on the loop rule, that is the epsilon 1 minus I'm not epsilon, E1 minus the I1 R1, the same as I1 R2. So now from that, R2 is E1 minus I1 R1 over R2. I'm sorry, I1. I'm sorry, I1. Right. So the I1, I mean E1 is 6 volt constant value, and I1 is 0.1, and R1, we already found the R1 from B, that's 20 ohm. And I1 is 0.1 amps from the graph. So you plug that all the number, then that should be 6 minus 2 over 0.1. So that is 40 ohms. So R2 is 40 ohm out of the graph. So you can find any point, you can pick up any point to actually find the values, because the E2 basically varying based on this graph. So this is a linear actually the graph to provide all the values you need to drive the values of unknown parameters of this circuit.
Wait, for the loop rule, why did you add the resistor to the, like, how do you know which direction the resistor is going to go?
The loop 2, right? Are you
No,
talking
for
about
the very
this one?
like the very beginning, you said E2 or EMF2 plus I1 times R1 minus EMF1 is equal to 0.
Mhm.
How did you know to add the resistor? Because how do you like know the direction of the resistor?
Oh, see that this E1 is the plus the minus, right? So that indicating that the direction of this E1 is upward, so they produce current in this direction. But I choose the loop of my loop rule is the counter, I mean the clockwise. So from that, the E1 is, E2 is also produced current is upward. So with that idea that E2 is the same direction of loop, so that E2 comes with a plus sign. And but if you look at this R1, the current produced by the E1 is opposite direction of a loop, right? So that should comes with the plus sign. So if the current is opposite direction with the loop along the resistor, that resistor produced positive sign, should comes with a positive sign.
Okay.
So then, and also, if you look at this direction, the loop, then the loop and this resistor, I mean the battery, this loop direction, and this E1 in opposite direction, right? Because the current produced upward, but the loop direction is downwards. So that should comes with the E2, E1 should comes with the minus sign.
Yeah, that makes sense. Also for the current one, you
Mhm.
said it's less than 0, as long as E2 is greater than E1, and I was wondering like where you got that from.
This problem or previous problem?
This one, it says current one is equal to EMF1 minus EMF2 over R1 is less than 0.
Oh, I'm just telling you, in case that E2 is bigger than E1, then obviously I1 should be minus value. You see that this especially, hold on. From the loop relation, this one, first this equation, you can drive this formula I1, right?
Yes.
And if the E2 is the varying EMF, right? The value is varying as you can see in the graph, right? So 6 volt is the reference point. If E2 bigger than 6 volt, it's the E2 is bigger than 6 volt because E1 is 6 volt, right? E1, I believe that is to set up the where is it? Value E2. Oh, I don't see that. Oh, not 6 volt. Any part of like this graph, if the E1 is smaller than E2, then I1 should be negative value. Does it make sense? So like I1 is just given by the relationship between the E1 and the E2 by this formula. Obviously, R1 is positive value. So whether or not this I1 is negative or positive, it depends on the relative value of E1 and E2. E1 is bigger than E2. The area of E1 is bigger than E2, then I1 is positive value. But if I1 is smaller than, E1 is smaller than E2, then current I1 should be negative value. Let me rewrite it. So hold on a second. So let me delete of it. Delete it. So the first, you understand that how the I1 is given in this expression, right? From jump, loop law. So I1 is E1 minus E2 over R1, right? So E1 itself is constant value, as is just only given in this equation. This problem, right? E1 is fixed value, but E2 is varying, as you can see in this graph. Values start just varying over some condition. So if E2 is smaller than E1, then I1 should be positive, right? But if absolute value E2 is bigger than E1, I1 must be smaller than 0, negative value from this formula. You're questioning that the meaning of negative value or positive value, or how this curve can be negative or positive?
No, that makes sense. Yeah. But also how do you use the graph to, like, as you go through the steps, I understand the equations that you used. But how did you get the values from the graph?
So here the solid black line is, as I said, I2. The IS, the y-axis IS indicating that the current value along the loop 1 and loop 2. Okay, so the IS itself is indicating current along the R1 and R2. Okay, so the y-axis is just like a global notation indicating the current value on R1 and R2. So the dashed line I1 and the solid line I2. That is given condition, right? And depending on E2 value, the value of the battery E2, you can actually pick up any numbers. So basically, you can choose the 4-volt, 5-volt, or 6-volt, any volt. You can choose any numbers to find out the E1, R1, and R2.
So for like something like part B where it says resistance R1, how did you get EMF is equal to 2?
2 volt?
Yeah.
I didn't get it. I just choose it because that's easy number to find out. E2, I choose it to find that I1 value and I2 value from that.
Oh, because they're linear, so they're gonna have the same.
Yes. That's the linear formula. You can easily find it just because You can choose the 3 volt or 1 volt, any volt, but if you choose the E2, the 2 volt, you see that you can easily find the number of value of I1 because it's just cross over, cross that the finite number of I1. You can easily just calculate the number of R1. If you choose you can, as I said, you can choose maybe like maybe 1 volt, but it's hard to tell. This one is maybe like 0.15, 0.13, or 0.14. You don't know. But if you choose 2 volt right there, this is 2 volt, right? That is just right on the 0.2 amps of current I1. Because this graph, this grid actually just showing you just exact value of I1 and I2 if you choose a specific value of the E2. So this is not the number I found. It's just I choose this number to find out I1 from this graph.
Okay, and then is this the same thing for part C?
Yes, see the same thing. I choose where is that? C. I choose the 6 volt. I choose 6 volt because it pick up the 6 volt. I1 is 0, right?
Yeah.
And no, that's the 6 too. Let me double check. I'm sorry, the E2, the 4 volt. If you choose the 4 volt, then the I2 is 0, right? Just come across that the 0 value. So I2 is obviously 0, and the I1 is 0.1 amps. But you can choose 5 volt, you can choose 6 volt, doesn't matter. But I choose that this is a linear formula, linear equation. So this graph just is reference to find out numbers you need to solve this problem. Okay, so you just need to very carefully look at the graph and then dig out the numbers you need to solve these problems, so that the value of E2 is not driven from any formula, any equation. I just picked them up and to find the current value out of that.
Mm-hmm.
Okay, so it's part of the condition provided by these problems to solve the equation. Do you have any other question, or does it make sense?
No, it makes sense.
Okay, good. All right, let's move on. This is parallel and series connection problem. So maybe I can read this problem and then solve together. So number 40, 2 identical batteries of EMF 12 volt and